Section 16.3 Radiation Measurement. One of the most common instruments for detecting beta and gamma radiation is the Geiger Counter. It consists of a metal tube filled with gas such as argon. When radiation enters the window on one end of the tube, it forms charged particles in the gas, which produce an electrical current. Each burst of the current is amplified to give a click and a reading on a meter. Measuring radiation. Radiation is measured in several different ways. When a radiology laboratory obtains a radioisotope, the activity of the sample is measured in terms of number of nuclear disintegrations per second. The Curie, the original unit of activity, was defined as the number of disintegrations that occurred in 1 second for 1 gram of radium, which is equal to 3.7 times 10 to the 10 disintegrations per second. The unit was named for the Polish scientist Marie Curie, who along with her husband Pierre discovered the radioisotope elements rubidium and polonium. The SI unit of radioactivity is the becquerel, which is 1 disintegration per second. The rad, or radiation absorbed dose, is a unit of measured the amount of radiation absorbed by 1 gram of material such as body tissue. The SI unit for absorbed dose is the gray, which is defined as joules of energy absorbed in 1 kilogram of body tissue. The gray is equal to 100 rads. The rem, or radiant equivalent in humans, is a unit that measures the biological effects of different kinds of radiation. Although alpha particles do not penetrate the skin, if they should enter the body by some other route, they can cause extensive damage within a short distance of tissue. High-energy radiation such as beta particles, high-energy protons, and neutrons that travel into tissue cause more damage. Gamma rays are damaging because they travel a long way through body tissue. To determine the equivalent dose, or REM dose, the absorbed dose is multiplied by a factor that adjusts for biological damage caused by a particular form of radiation. For beta and gamma radiation, the factor is 1, so the biological damage in REMs is the same as the absorbed radiation in RADs. For high-energy protons and neutrons, the factor about 10, and for alpha particles, it's 20. So biological damage, REM, is equal to the absorbed dose times a factor. Often, the measurement for an equivalent dose will be units of millirems. 1 rem is equal to 1,000 millirems. The SI unit is the sievert. 1 sievert is equal to 100 rems. Table 6.4 summarizes the units used to measure radiation. People who work in radiology laboratories will wear film badges to produce their exposure to radiation. A film badge consists of a piece of photographic film in a container that's attached to clothing. If gamma rays, X-rays, or beta particles strike the film, it appears darker upon development. Periodically, the film badges are collected and developed to determine if any exposure to radiation has occurred. Exposure to radiation. Every day we're exposed to low levels of radiation from naturally occurring radioisotopes in the building where we live and work, in our food and water, and in the air we breathe. For example, potassium-40, a naturally occurring radioactive isotope, is present in any potassium-containing food. Other naturally occurring radioisotopes in the air and food are carbon-14, radon-222, strontium-90, and iodine-131. The average person in the United States is exposed to about 360 millirems of radiation annually. Medical sources of radiation, including dental, hip, spine, and X-rays, mammograms, add to our radiation exposure. Table 6.5 lists some common sources of radiation. Another source of background radiation is cosmic radiation produced in space by the sun. People who live at high altitudes or travel by airplane receive a greater amount of cosmic radiation because there are fewer molecules in the atmosphere to absorb radiation. For example, a person living in Denver receives about twice as the cosmic radiation as a person living in Los Angeles. A person living close to the nuclear power plant normally does not receive much additional radiation, perhaps zero point 0.1 millirem in 1 year. 1 rem equals 1,000 millirams. However, in the accident at Chernobyl nuclear power plant in 1986 in Ukraine, it's estimated that people in nearby towns received as much as 1 rem per hour. Radiation sickness. The larger the dose of radiation received at one time, the greater the effects on the body. Exposure to radiation of less than 25 rem usually cannot be detected. Whole body exposure of 100 rem produces a temporary decrease in the number of white blood cells. If the exposure of radiation is greater than 100 rem, a person may suffer the symptoms of radiation sickness: nausea, vomiting, fatigue, and a reduction of white cell count. A whole body dosage greater than 300 rem can decrease the white blood cells to 0. A person suffers diarrhea, hair loss, and infection. Exposure to radiation of 500 rems is expected to cause death in 50% of the people living at that dose, receiving that dose. The amount of radiation to the whole body is called the lethal dose for 1/2 of the population, or LD50. LD50 varies for different life forms. Table 16 shows whole body radiation of 600 rems or greater would be fatal to all humans within a few weeks.